Welcome to 12.1 in Algebra. This chapter we're going to be talking a lot about rational expressions and how to turn something into a rational expression. But today we're talking about inverse variations. So we're in 12.1, page 642, and we're going to start reading about graph inverse invariations. Recall that some situations in which y increases as x increases are direct variations. So as x increases, y increases. And that's our very standard positive slope graph. Just as x increases, y increases. As one goes up, the other goes up. That's our direct variation. If y varies directly as x, we can represent this relationship with an equation in the form of y equals kx. Y equals kx. And this is direct variation. That just means whatever k is, you multiply it by x, your y is going to get bigger. So 3 times x, bigger. 4 times x, bigger. As x increases, y increases. However, in the application above, one value increases as the other value decreases. So in that case, as x goes up, y goes down. As x goes up, y goes down. The gap between our two variables is getting bigger. When the product of two values remains constant, the relationship forms inverse variation. We say y varies inversely as x, or y is inversely proportional to x. Inverse variation, key concept. Y varies inversely as x if there is some non-zero constant k, such as x, y equals k. So our formula here is y is equal to the product of k and x, where k is a constant, and that's direct variation. And now they're presenting us with a new formula. Y times x equals k, where k is a constant. That means it's not changing. It'll be the same value time and time again. And if we end up with a formula that looks like this, we're said to have indirect variation. Direct variation again means as one gets bigger, the other gets bigger, and we're walking up the ladder together. But if we find ourselves with x times y equals k, where k is a constant, meaning a number, an actual number, then as x gets bigger, y gets smaller. Or as y gets bigger, x gets smaller. We're walking in opposite directions down this ladder. Let's look at example 1, and we're going to talk about what this actually means. Graph and inverse variation. Driving. It takes time, represented by the variable t. The time it takes to travel a certain distance varies inversely at the rate at which you're traveling. So that means the faster you're going, so the faster the miles per hour, the less time it takes to get there. So the faster you're going, the shorter the minutes it'll take. The equation r times t is equal to 225 can be used to represent driving 225 miles per hour. So this is our constant rate. No matter what, you are driving 225 miles per hour. Complete the table below to draw a graph of the relation. R is your rate, t is your hours. So the rate at which you're going times time, how long it's going to take. Solve for your values of r. Or solve for r equals 5. And now I've only copied part of the graphs because we're going to stick with whole numbers just to help this move along faster. So they're saying solve for r equals 5. So if you're traveling at a rate of 5, how long is it going to take, set next to the constant of 225? We're solving for at 5 miles per hour. How long is it going to take? Get t by itself, so divide out your 5. Divide out your 5. T equals what? T equals 50. It is going to take us 50 hours to be able to travel the same distance if we are only going at a rate of 5 miles per hour. And now we're going to keep going. Let's say we go a little bit faster. Let's say our rate is equal to 10. So 10 times t, because that's our original formula, is equal to 225. We want to know how long it'll take, what will be our time, traveling at this rate, divide by 10, t is equal to 25. So again, as our rate gets faster, we went from 5 to 10, our time is getting slower. We're going from 50 to 25. We're starting to see an inverse relationship. One's getting bigger, the other's getting smaller. Let's try 25. 25 miles per hour is going to be the product, or 25 times time is going to equal 250. Divide out your 25. Cancel that out. And t equals what? T is equal to 250 divided by 25, which is going to be equal to 10. Again, we're getting bigger up top, but our numbers are getting smaller on the bottom. One last one. Where is my eraser? We have 50. So if we're going at a rate of 50 times t equals 225, how long will it take us to travel the same distance if we're going 50 miles per hour now? T is now equal to what? T is equal to 5. This relationship is modeling our inverse relationship, that as our rate gets higher, so as it gets faster and faster, the time it takes gets slower and slower. So what would this look like if we were to graph it? If we come over here and we look at our graph, I've labeled it every other, and it's going up by units of 10. So my first two blocks, 1, 2, is going to be at my 10 mark, 3, 4, 20, 5, 6, 30, 7, 8, 40, so on up to the top, with my highest value being 50. And I'm just going to model this. That if my rate is on the bottom, time is on top. So, if my rate is 5, starting right here, if my rate is 5, and I'm going to go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Perfect. Alright, so if my rate is 5, that means I'm all the way up here at that point. Next, I'm at 10. At a rate of 10, it takes me 25. So it's going to be right here in between my 30 and my 20, right there. Next, if I have a rate of 25, 5, 10, 15, 20, 25, I'm going 10, it's taking me 10 hours. And now lastly, if I'm going at a rate of 50, which is going to be all the way right here, it is taking me 5 hours. And so I'm coming up with this beautiful kind of C crescent shape. And that's what inverse relationships are going to look like. They're going to look like this nice little curve downward along your x and your y axes. But the thing is, if we notice, all of my x and y values are positive. All of my values are going to end up in my first quadrant. But it's not always the case that all of my values are going to be positive. If I'm working with negative values, you're going to find an axis of symmetry between your two graphs. And they're all going to end up in your third quadrant. And we're going to move on to the next and see what that looks like. We're going to go to example 2. And that's going to model positive and negative values and how that plays out into our graph. And like I said, positive values are going to end up in quadrant 1. Negative values are going to end up in quadrant 3. And they're going to be mirrors of each other. Alrighty, so now on page 643, graphs of inverse variations can be drawn using negative values of x. It doesn't have to always be positive. Remember, x is your input, y is your output. Example 2, graph an inverse variation. Graph an inverse variation in which y varies inversely as x, y equals 15, x equals 6. So let's talk about what that means. They're telling us we have an inverse variation. They're taking some guesswork out for us. We have an inverse variation. Inverse variations always follow this formula. X times y is equal equal to k, where k represents a constant value that does not change. It will always be set equal to whatever k is equal to. And then they tell us y equals 15 and x equals 6. Well, perfect. I don't know what k is, but I know k is equal to y times x. So if y is 15 and x is 6, plug those in. 15 times 6 is equal to k. 15 times 6 is equal to 90. So 90 is my constant. My value for k right here is 90 for this particular problem. If they tell me, from the beginning, that they're giving you the value of y being 15, the value of x being 16, and they don't tell you your constant, all you have to do is multiply these two numbers together to get your constant. And so now I know, for this particular problem, any product of x and y has to equal 90, because 90 is my constant. X and y change every single time, right? As you continue on a graph, you put in a new value for x, you get a new y. Put in a new value for x, you get a new y. However, k is our constant value. It will always be the same. So any value you plug in for x and y has to equal 90. So let's look at the graph they give you in your textbook. They're going to give you positive values and they're going to give you negative values, and they start with your negative values. So they say here is your x, here is your y, and just like with a linear equation, the same is true for inverses, that your graph will go on infinitely. There is no cutoff point. So it's not one of those things that, oh, I don't know what x is. Well, x can be equal to anything because your graph goes on forever. But for this particular instance, your x and your y values have to be the product of 90. So if I'm starting with my negative values, if I say let x equal negative 9, well, x times y has to equal 90. So negative 9 times what equals 90? It has to be negative 10. Negative 9 times negative 10 equals 90. I'm going to keep going. I'll use the values that they gave me from the very beginning to prove what my constant was. I'll say, okay, what about negative 6? Negative 6 times negative 15 equals 90. Very good. What are some other values I have? I have negative 3 and I have negative 2. Negative 3 times what equals 90? Negative 3 times negative 30. Negative 2 times negative 45. All equal 90. So I've come up with all possible negative values for x and y that produce a positive 90. And then I'm going to keep going. What happens if I plug in 0? If I plug in 0 for x, 0 times y is equal to 90. And I'm going to end up canceling it out. The only way to get y by itself is to divide 0 onto both sides. Y is equal to 90 over 0, and that doesn't exist. There is no such thing as division by 0 right here. That is simply called undefined. So that value doesn't exist. There will never be a point at 0 in an inverse variation. And now we keep going, and we're going to go through our positive values, because we're still trying to get to 90. So that means I could have 2 times 45 is equal to 90. 3 times 30 is equal to 90. 6 times 15. And then lastly right here, I can have 9 times 10 is equal to 90. And all of this belongs to the same graph. I just have a breakpoint. I have a breakpoint along my x-axis because I have 0 as undefined. So let's see what happens when we go to graph this. Using these same little post-it notes to help us along. And then we're going to change our x-axis to be increments of 1, so 1, 2, 3, 4, so on and so forth. So starting at the very top, I have negative 9, So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it's at negative 10. So my point is right here. Or, whoops, going by 2's. Right here, right? 1, 2 is 10, so 1, 2 is negative 10. Then I have negative 6, 15. So negative 6, 1, 2, 3, 4, 5, 6. And now I need to go down to 15. So here was 10, here is 15. Keep going. I have negative 3, 30. 1, 2, 3. And now I need to go down to 30. So negative 10, negative 20, negative 30. And then I have negative 2, 45. 1, 2. My 45 is going to be about right here. And now you can see the same curved shape. That we end up with this crescent traveling between our points that brings us close to our axes but doesn't touch them. Alright, I'm going to run out of these on this next one, but I'll just draw dots. So we have 0 is undefined, so nothing is going to be right here, but now we keep going. We have positive 2, 1, 2, and it's at the 45 mark. So that is 40's here, right here. And then our next one is going to be at 3, 30. So 1, 2, 3, up to 30, 6, 15, 3, 4, 5, 6. Then it's at the 15 point, which is right about here. And then we're at 9, 10. Yep. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Right there at 10. And you can see a perfectly matched crescent in our first and our third quadrants. Remember that I said at the very beginning, you can have both positive and negative values. Your negative values for your x are always going to put you in your third quadrant. Your positive values are always going to put you in your y, or not your y, your first quadrant. And if I were to draw a dashed line right down the middle and fold my paper on that diagonal, I'd have an axis of symmetry. My two graphs are perfectly symmetrical on both sides in my first and my third quadrant. Mouthful. Alright, now we're going to go forward with using inverse variation. And this is going to be a proof that I'm going to show you for what you can use to solve for unknown values as you go forward. So we've learned what an inverse variation is, we've learned how to graph it, and now we're going to say, how do we use this algebraically? How will this come into play if we don't know a value? Because that's what they love to do in algebra, right? Give us an x instead of a number. Just kind of the name of the game. So I'm going to erase, and then we're going to walk through the proof at the bottom of the page, and then we're going to move to the next page to look at the example of it. So as I've told you, inverse variation is x times y is equal to k. And any single value you plug in for x and y has to produce this constant. So let's say I plug in one value, x1, y1. That has to equal k. Just like negative 9 times negative 10 had to equal 90. But then I plugged in another value. I said, okay, I'm going to do a second set. x2 times y2 similarly has to equal 90. And then you keep going through it. x3, y3, x4, y4, all equals 90. But if every pair of ordered pair equals the same thing, then you can almost set your ordered pairs next to each other. So if both of these multiply together to equal 90, then they multiply to be the same thing. So I can just as easily say x1 times y1 is equal to x2 times y2. And remember, our previous example, we had for our first xy value, negative 9 times negative 10. And for our second value, what did we have? We had negative 6 times negative 15. Well, negative 9 times negative 10 is equal to positive 90. Negative 6 times negative 15 equals positive 90. So I haven't changed anything by setting them next to each other. I've just taken two equal statements. This times this equals 90, this times this equals 90. Well, if they both equal 90, then multiply them across, they're still all equal to 90. So this is our first proof for using and solving inverse variation. y1 times x1 is equal to y2 times x2. That's our first one. But we can then derive this further and say, okay, what if I wanted to do a proportion rather than solving it algebraically? So we'll just say this is method 1. Is just to memorize x1 times y1 is equal to x2 times y2. And now we're going to look at how to come up with method 2. And when I say method, this is all a method for what happens if they give you 3 out of these 4 values and you have to solve for the 4th. You could choose between these methods. Alright, we're going to go back to this original problem and look at how they come up with their second method. So we're back to y1 times y2 equals x2 times x2 times y2. And they're going to say, okay, well, what if I set it up with a proportion by canceling things out, by turning this multiplication problem into a proportion? That way I can do my cross products and solve for it. In order to do that, we're going to divide each side by common factors to see if we can get it stacked a little bit differently. So it doesn't matter which ones you pull, but you need to pull one from each to divide out. So what I'm going to do is to mirror their book, and they say, use the product rule for inverse variations and divide each side by x2, y1. x2, y1, x2, y1. And again, you could have done y2, x1, y2, x1. Doesn't matter, but you just have to pull something from here and something from here to divide out because you're trying to get something to cancel. As is currently written, my y1's cancel, my x2's cancel. And now I have the proportion x1 over x2 is equal to y2 over y1. And this is going to be the exact same mathematically once you plug things in as our first method of x1 times y1 is equal to x2 times y2. So method 2 is to use a proportion. x1 over x2 is equal to y2 over y1. I will say this isn't my favorite just because you have to keep straight that this is x2 over x, or x1 over x2 equal to y2 over y1. Notice your crosses are your 1s and your crosses are your 2s. I do think this is the easier method for keeping your numbers straight, but we'll do an example for each. Alright, so example 3, solve for x. Alright, example 3. We're going to do both of them, method 1 and method 2. So y varies inversely as x. So we have an inverse relationship, that's what that italicized phrase says. And y equals 4, x equals 7. Find x when y equals 14. So one more time. If y varies inversely as x, and y equals 14 and x equals 7, find x when y equals 14. So we're going to take the information they give us and we're going to turn them into values. So we're going to say, okay, what's the first x value they give us? What's the first y value they give us? What's the second x value they give us? What is the second y value they give us? So they tell us y equals 4, x equals 7. So y equals 4, x equals 7. Cool, we have our x1 and our y1 value. Then they say find x, find our second x value when y equals 14. So just like I said, they've given us 3 out of our 4 numbers and we have to solve for our 4th. So if we're using method 1, what will that look like? Method number 1, that means we take x1 times y1 and set it equal to x2 times y2. Alright, x1 is 7, y1 is 4. We don't know our x2 value, so we're just going to leave that as is, times y2, which is 14. 7 times 4 is 28. 28 is equal to x2 times 14. Our goal is to get x2 by itself, so we have to divide 14 out onto both sides. 14 cancels, put 14 over here. 28 over 14 is just 2. So 2 is equal to x2. And again, that's a subscript, it's not x squared or anything like that. It's just to designate our second set of x's. So we know x2 has to equal 2 in order for it to be a true statement. But let's now look at method 2 for the same problem. Again, we don't know our second x value. We now know it's 2, but for the sake of the argument, we don't know. Method 2 says we're going to take x1, put it over x2, set it equal to y2 over y1. And this is what I meant. You have to remember your diagonals have the same number value. 1 and 1, 2 and 2. Alright, so x1 is 7. We don't know x2, so that's staying here. y2 is 14. And y1 is 4. And now we're going to use our cross products to solve for x. So we're going to end up with 7 times 4 is equal to 14 times x. 7 times 4 is 28 again. Set that equal to 14x. Divide 14 out onto both sides. 2 is equal to x. So both method 1 and method 2 will bring you back to the same answer. It's just which one you think is simpler. Like I said, I think method 1 is simpler, but you're welcome to use method 2 as well. Alright, let's look at example 4 now. Example 4 says, solve for y. If y varies inversely as x, y equals negative 6 when x equals 9, find y when x equals 6. So step 1, list out the values they give you. So example 4. We need an x1 and a y1. We're looking for an x2 and a y2. And on this one, our y's are unknown value. So as they tell us, if y varies inversely as x, and y equals negative 6, so y1 is negative 6, and x is 9, so x1 is 9, find y when x is positive 6. So we're going to use x1 times y1 is equal to x2 times y2, and plug in our unknown values. Or not our unknown values, our known values. So if x1 is equal to 9, 9 times y, which is negative 6, is equal to x2, which is 6, times y. 9 times negative 6 is going to be negative 54, is equal to 6y. Get y by itself by dividing out 6. And I would have negative 9 is equal to y. And so I was able to solve for my unknown value. We're going to stop there for today, and you are now going to be good to do your homework. Good luck.